Okay, hi everyone. So this is um, what I'm currently working on. So I had an exam on databases and on software tools and technologies, and the next exam I have is on operating systems, and then there will be introduction to data science, and then there will be compilers. So for compilers, it's not really an exam, more like a miniature exam where there's only 10% weightage to it, and so I'm just going to read something that will help in the project. That's all. That's all I'll do. But so data science is something which I really want to do correctly. But before that, I have operating systems, which I also want to do correctly. It's just that the course is a bit unstructured and there's a lot of bad stuff that's happening in the course. So I'm a bit put off, right? So another thing which I wanted to say was this whole semester I've been struggling with putting my focus into things, mainly because there's this one realization that I had, which I mean, it's kind of stupid that I didn't have the realization earlier. And that's like, since nobody cares, they also don't care what kind of grade you're going to get. So the one motivator which I always used to have at the end of the day, that you still have to do it because, well, grades, or because people will laugh at you, or because society won't accept it or something like that, now it's gone. Yeah. So now I don't see it that way. I see it like, okay, I'll be rewarded a grade based on however they see what I did, which will be like completely orthogonal to what I will actually do. Although there's a bit of correlation, but I'm going to assume it's going to be completely orthogonal. Worst case scenario. And so what do I do it for? I can't be doing it for grades because that's shallow and kind of useless, right? I mean, having a 9 plus CPI is, I mean, it's good enough. You don't need to be like 9.5 plus or like 9.7 or something like that. But yeah, just having a simple 9 plus CPI at the end of your 4 years, that's probably enough to sit in placements for any sort of company, or whatever sort of thing that you want to pursue. You can probably pursue it if you are decent enough, if you're not like a complete joke, like you have a CPI of 6, which probably can only happen if you really messed up. Like, I don't know, you just didn't go to the class at all, any class in fact. I mean, that's kind of a rare occurrence. That happens to people who really like were not present in the first place, who didn't even try. So I don't think I'm going to get something like that. Like, and so being just average is fine by me at this point. Like, at some point I used to really want to be like, you know, the best, like get highest grades, or get the best output possible, or do this kind of projects and all these things. And now I don't want to be that, because I've been that multiple times, and I realize it's kind of lonely there. Like, you put all this effort, and in the end, all you get is just a stupid letter. So is it worth it? I mean, it does not actually practically change anything for you. So is it really worth it? In the end, like, anything materialistic is, after a certain point, is not going to really change anything for you. Like so what if you get lots of money? So what if you buy cars and all these things? In the end, all you really need to be happy are just the basic requirements, right? Or maybe a AC, like put that in. So if you're living in a very hot climate, that might be another necessary requirement. But yeah, so you have all that. If you have all that, then there's literally like nothing that you need apart from it. Anything you need can only be described as a want, or some sort of compulsion that you have, or something emotional, like related to your worth, or like something like that. And that's unhealthy. I think it's not a very good way to look at it, because what happens if you don't get it? And that will happen sometimes. That's just how it is. Like, people want something and then they don't get it. So at that point, like, your whole self-image is destroyed because you're not getting something which you want. And you know who else goes through these kind of tantrums? Like, they're not getting what they want, so they'll be like very problematic people. Children. Yeah. And I don't want to be that child who throws a tantrum because he didn't get what he want. And so I'm going to think less of these more materialistic and luck based things, right? I'm saying grades are luck based because, well, they are. um, if you didn't start out strong, if you didn't have all the knowledge and the drive, it's not your fault. It just happened that your circumstance wasn't correct, or you didn't have good teachers or anything like that. It has nothing to do with your actual ability, and I've seen that time and time again. People who society assumes are like really bad at this, um, they actually have a lot of latent potential. It's just that they don't ever show it because they're so in their head that they're thinking constantly that, oh, society will laugh at me if I try and fail and all that. And like, they'll laugh at you anyway, right? Even if you don't try. In fact, the worst part is they won't even laugh at you, they'll just not care. Nobody will look your way, right? Unless like at the top of the race, nobody's going to look at your way. And even if you are at the top of the race, they're looking at your back. They're not looking towards you, like your face. You will never be able to see other people when you are at the top either, right? So it's all lonely. Like there's no escaping. There's no good ending. It's not like you'll work hard and then you'll get the thing, or get all the good things in life and then it'll be a happy ending. No, you work hard, you get all the good things, and then you realize, oh, none of this actually matters, because you want something even more artistic, something more romantic than all of this. And I'm saying romantic not in the the usual romantic relationship sort of way. I'm saying something which ties into like your aesthetics and all that. So you just keep wanting more and more and more, and it won't stop, and you know it. So if you are really going to do something, you might as well do it for yourself, and not for these abstract and not for these arbitrary notions that people have of what's worth and what's not worth, and what's intelligent and what's not. Because at the end of the day, you can't ever claim that you're intelligent when all you did was just take ideas which people already had created before you and then just incorporated those ideas in yourself to pass a test. Is that intelligence? Or is that just the capacity that a human has? I mean, sure, you're determined, like you are a hard worker and all that, and it shows, right? You want to get it done. Sure, you're more or less a perfectionist, and people would love to have a guy like that hired. But are you intelligent? No. I guess the only people who really are intelligent are people who come up with their own theories, who come up with ideas. Like, I could literally say that artists are intelligent because they are very creative. I could say that people who solve real world problems are intelligent, right? So proper engineers, they are very intelligent. I mean, engineers who actually like create new systems and all, so they are intelligent to some degree. And yeah, everyone else is like, okay, you're a hard worker, you can learn fast, you can figure out stuff, but you're not creative, you're not doing anything on your own. So are you really intelligent? Can you call ChatGPT intelligent? Well, some would say yeah, and if that's how we define intelligent, good for you. You are a pretty intelligent person yourself by your own definition. But I would not define it that way. I want to define it with creativity. Define it like you want to do something which inspires you, or something which you cannot stop doing. It's compulsive, and you have ideas in your head and you're struggling to keep those ideas down, and you just want to do so much. That's kind of how I want to be, right? I don't want to be this person who is perfect in all ways and gets good grades and all. Not goody two shoes. Alright, enough of a rant. Let's just get into it. Oh, I chose the wrong things. Operating systems. Yeah, so we just did piece 1, and then there's something about concurrency, but that's pretty much it. So I think in the first part I already did like virtualization, but just to go over it, so basically you have abstraction. So that's like you are going to virtualize in 3 different ways. You can virtualize the CPU, the memory, so the RAM basically, and then you can also virtualize the file system. So like you can virtualize the disk space into files. Right, so then you have the process API, which so I'm just going to read this whole thing actually. The address space is just the code heap stack. Usually it's segmented into 3 segments. Each of them have like a direction bit. Each of them have an identifier. So it's like 2 bits are required. So it's like to identify which segment you are in and all that. They all have like their own base form registers, etc., etc. We know it. The heap is small at first. Repetition of malloc causes OS to come in, etc. Using free will remove that memory, etc. This fragmentation which you have to worry about. You have to do compaction time to time. The best way to reduce fragmentation is to using paging or something like that. So basically, pages are like fixed size blocks of memory which are allocated to these programs or segments, in fact. And so like every process has its like page block sort of thing. It's like it has IDs for different pages, and then based on that you translate the virtual address to the correct address, etc. So then you have the process states, so like 5 states. You have the start state, which is the process has just started, so it just starts in the start state. Then it goes into waiting state straight up, and then it goes into the running state. And from running state there are 2 possible things. You can either go into an IO wait state. So okay, I shouldn't have said waiting, it should be a ready state. So you straight up go to a ready state. It's like an epsilon transition. So you just straight up go to the ready state, then at some point you go to the running state when the OS picks you up, and then you run. And then there are 2 options. You can either go into waiting state by doing a IO operation or a system call or whatever, or you could go into the end state, so like you kill yourself or something like that. So or some other process kills you, that could also send you to the dead state. So once a process is dead or terminated, its process struct is not like destroyed straight up, right? The reason is its process ID should be available to the parent, right? So sometimes you do a pthread join. Okay, that's not a thread, sorry. You do a so you do a fork, and then you wait for the process to complete. It's like a wait or wait PID or something like that. So you want the process to return or change your status, right? And then the parent process should be able to figure that out. And once that happens, like you can finally terminate the whole process. So there are 5 states basically: running, ready, blocked, or waiting. And you also have start, and yeah, it's in the final state. So just some API thing. So it's like whenever you call fork, it returns a code, right? So to do a fork, you just like literally just call fork. You don't. So where's the process API? Yeah. So fork, just call it like normally. And then you have wait, which is like it's gonna wait for every single process for it to complete, and then it's gonna move on. And you can do a wait PID, which like waits for a particular PID. So this fork thing actually returns the process ID as the return code. And then so if it's 0, then it's basically like you were the child who is created, and if it's not, then you know which child was created. So every process has like its own process struct. So basically like OS is written in C in the end, like Linux kernels at least, they're like written in C. So we're just dealing with like some program which has variables and everything. So process struct is basically just a variable. It's like you define a struct for a process, and then that thing has all the things you would need. You have the base bound registers for different segments, you have its ID, you have its current status, you have some other things like its registers, like machine state and all that. Alright, so when you do a wait or wait PID, it waits. When you do an exec, so it like runs another compiled program, so like for a different file. So using code sharing, you can actually like not just like copy the program and then run it. No. So usually what would happen is like you require a new address space or something like that. But this time, so when you do an exec, what happens is is that just like it's okay. So how do I actually explain this thing? Good question. Yeah, I mean, it just in the end like makes it program counter point to the code section of some other function that you have built up or something like that. So that's what execute does. But yeah, kind of forgotten what this does exactly, but this is fine. So I'm saying it's gonna kill the current program, but what it really does is like it overrides by adding another code section and then makes a program counter point to that, right? So the previous code section is still there. So if you're using like code sharing or something, then at that point the code is not like deleted, but you just have another process set up which like now points to a different code section. So it's like its program counter is different. That's all that's happening. It's stack. Okay, so you're not dealing with threads, so there's a different stack altogether. Fine, but the code is not a different thing. That's the only thing. Fine. Let's process API. It is fork, wait, execute. So there's highly intelligent policies make the mechanism faster. That's address spaces. So the code is going to go downward, so like it grows into higher memory spaces. Your stack goes up, your heap also goes down. So code and heap are to be like copied every time you make a new process, but then stack and heap are to be copied every time you make a new process, but code can be shared if you are using segmentation or something. All right. Process states, process list, save registers. Register context of a process thread is more like it. Okay, whatever. No, we don't need any of that. Process API, we did that. So these are very easy things. Limited direct execution, cooperative preemption is when the OS waits for the application to system call. Right. So fine. Timer interrupt. So it's like after every like delta t, a timer goes on, which is like OS comes in and it takes control or something like that. Kernel stack. So this is something you use for scheduling, like round robin or something. Kernel stack. So this is the visual stack in an address space which holds the value of the saved register for process. Every process has its own kernel stack. So whenever you want to context switch or to a system call, what happens is, so you have your address space, right? You have all the things. So what you would do is you would put all the registers, like you would save it in a kernel stack, right? So this is going to be like in your address space. In fact, you do that, and then you what happens after that? Oh yeah, right. So it's saved. Then from the kernel stack, it's like copied into some sort of hardware, if I remember. Oh, okay, no. So it's from the hardware. It's copied to the kernel stack, and from the kernel stack, it's copied to the process struct, right? So after the like OS comes in, it just takes everything from the kernel stack and it puts in the process struct. Once it puts that, so this requires the CPU to be occupied by the OS. So that's why like it's a hardware sort of instruction to put everything into the kernel stack. So it's like some space which you have for this operation. So you just basically store it somewhere into the address space because it's already like given to the program, so might as well. And then the OS gets the control. So you switch to kernel mode, you copy the stuff into the process structure because only the OS can do it. Only the OS can copy stuff into the process structure. Once that happens, you do the switching thing, you do the whole scheduling. So okay, you firstly handle the interrupt. So if it's like it's trying to produce something or consume something or whatever, just do whatever it wants to, then you do the context switching. So the whole system call thing is something that OS has to do because only the OS can do system calls. Only it can like do IO operations or all these things. So it does whatever it has to, then it does a context switch. So it takes the process structure of something else, some other process, right? It puts whatever is in the process struct thing into the kernel stack. So OS has complete control over like all the address spaces, so it knows what to do. So it puts that into the all the registers in the kernel stack, right? So from the process struct, basically takes the process struct, puts in the kernel stack. So now the address space has all these registers, and then once again you give the control to the new process that you want to context switch to. So there's some sort of hardware instruction which like loads everything from loads all the registers from the kernel stack into the CPU, and boom, just as you load like everything from the kernel stack to the CPU, you have done the context switch, right? So now it's not the OS anymore. Now it's the process which is going to continue. So because your program counter points wherever it does in that process because it was like part of the register set. So you do that, and now you have context switch successfully into another process. So this is the full system call thing. So you save registers to kernel stack, switch to kernel mode, run the call. Okay, there's another step you have to store in the process structure, but like whatever. Switch to kernel mode, store in process struct, store registers into process struct. Alright, you run the call, you do a return from trap handler, you restore the registers and switch back to user. Right, okay, so this is like you have to move registers from process struct to what? To the kernel stack. Then you restore registers and you switch back to user mode. So this happens automatically, like, because okay, actually you should probably switch to the user mode first before doing this. I don't know, I mean, yeah, you probably should, and then you restore the registers. Actually, you know what, no, let's just say you do this thing. So you can probably program that like directly, I don't know, you can make the hardware such that like at the moment of switching itself it like switches to kernel mode. All right, just a second. Alright, so let's continue. And I'll have to stand up instead of sit down because like my legs are hurting now. But anyway, let's just keep going. Alright, so a system call goes like this: you save the register to kernel stack, you switch to the kernel mode, store registers to the process struct, run the call, run from app, move register from process struct to kernel stack, restore registers, and this happens every context, by the way. Restore registers and switch back to the user mode. Alright. So just once again, the timeline for a proper timer interrupt. Save registers to the kernel. Hardware does this automatically. Activate the kernel mode, jump to the trap handler, and now you call the switch routine. So this is where the scheduling and stuff. So this is where the system call like actually happens. So you jump to the trap handler. So yeah. So here we're saying like the system call does not have these switching to kernel, so like process struct stuff, but it does, because system calls don't just happen like without context. They also have like context switching over there, right? Okay. So activate the kernel mode, jump to a trap handler, call the switch routine. Right. So you save the register to process struct. So this is when okay. So it seems that the time you actually do the context switch is when you save to the process structure. Before that, you actually do the trap handler thing. Fine. Oh, so it makes sense. It makes sense because you may not need to like actually switch. In that case, it doesn't make sense to do all of this. So you switch to kernel mode. You don't do this straight up. You actually run the call. You return from trap. Yeah. If so it's like context switch. Context switch if needed, and then you restore registers, and then you switch back, right? So this this does a bunch of things. It does the changing of their address space, it like also like load stuff from the process struct to the kernel stack. So yeah. So you might say, why store it two times, one in the kernel stack and one in the process struct? And the reason you have to store it in the kernel stack so that when you switch over to the address space of the process, the hardware should like be able to identify where exactly is like all the stuff about the registers. So it just like picks up all the registers from there. So it's pretty easy if you do it like that, right? Yeah. So why storing the process struct? It's a good question. I don't think I have the answer for that. By changing the values of the stack pointer. I see. Into the other process. So this actually happens before the return from trap. Huh. So if we didn't do like a context switch, you would have just returned from trap into the current process, right? So you restore the registers of the other process from it, kernel stack, CPU. So hardware does this automatically. Then you activate the user mode. So the question is, why do these registers have to be stored in the process struct? And I don't know that, frankly. It's probably a reason for that. I don't know. So you have the stack pointer over there or something like that. Fine. So just the hardware knows exactly where all of that is. You can't just like leave it in the correct situation and then you would do it. Sure, that's one way to think about it. Why do you need a process struct to like store all of this? Okay. So what's a kernel stack again? What is a kernel stack? So we were told that every process has one kernel stack, and it's just like separate from the normal stack. So it's used to store the execution context of the user process. This context is stored before the return from kernel module. In short, nothing apart from using a different location memory. Okay. Copy from user memory. Okay. So kernel cannot trust the user space stack pointer to be valid or usable, therefore will require. Oh shit! So what you're saying is kernel stack isn't part of the address space of the user. I see. So it's, oh shit, so there's only one kernel stack, so it will be overwritten every time you, that's why you need a process struct to store it. That actually makes sense, because yeah, so when you do a timer interpret, it's not for sure that you will even have that memory allocated, unallocated. So you really have to do this thing. You have to have memory for the OS itself, where it will be able to store these registers. So like what the hardware instruction does, it takes stuff from the kernel stack and then it puts in the process struct. Sorry, it puts it in the CPU, right? Yeah. So you change the value of the stack pointer. So it's kernel of a particular process. Why would you have a particular process? Okay. So once again, kernels, so okay, I think I get it. So for every process you do have a kernel stack, except all of this is actually in the kernel space. It's not in the user's memory space. I see. So when you activate user mode, it's like just after the so this was so before you do the jump to PC thing, you return from trap to the other process. So I am assuming you mean the address space or something. We store registers of other process from the kernel stack to CPU. No, you are not jumping to that yet. It's still. So what is the return from trap? I don't know. Well, the good thing is at least that the kernel stack thing is so unlike process struct where it's like some object stored somewhere in the table, this is actually on the memory and it's like usable all the time. So I see. That's not to say that the process struct is actually somewhere on disk. It is on the RAM itself, but it's like an object. It's a proper data structure for storing stuff. This is just like a bunch of values in a stack. It's different. I see. Locking, yes, so that you don't have two system calls operating at the same time. It's a good idea. See. So disable interrupts during a system call and processing an interrupt. Even in general, for like just atomicity, you could be doing this. Alright, so that's LDE, limited direct execution scheduling. This is something which we know a lot. So again, just gonna go over it. What's the turnaround time? It's just like when you start, so when the process arrives, and when it ends. So it's like the ending minus the arrival. That's the turnaround. Your shortest okay, what's the response time? It's when it starts, so when it arrives versus when it like first starts to execute. So first execution time minus the arrival time. That's the response time. So I'm just gonna finishing minus the time of arrival. Arrival minus, okay, sorry, first runtime minus an arrival. Okay. So round robin is something which is the best for response time. Shortest job first to completion. So basically, shortest job first with preemption. That's something that's the best for turnaround time. It's provable, in fact. Round robin also is provable, like EQ1 equatability and all that. So it's that. And then you have multi-level feedback queue, which is like a hybrid sort of thing, which does both of these things. And then you also have a lottery system, which is probabilistic, and so it's never going to get stuck or something like that. Yeah. And there's sharing of priority. Cool, but this is going to be like since it's a probabilistic thing, you do not have, I mean, you do have fairness, but in a very probabilistic sense. You do not know for sure that it's going to run in a fair way, right? And that's where the stride scheduling comes in. So it's like the pass value thing. So you have a stride and pass value for each process, and like whichever one has the least pass value is the one which runs first. This has a problem that like whenever you get a new process, it just starts running straight up, and you have to earn these strides, etc, etc. So this like really, is bad because it just makes the new process run first and it like takes over the CPU completely. So yeah, it's bad. MLFQ is also bad to some degree. Then you have the CFS, which is like completely fair scheduler, which works on red black trees and all that. So why is the MLFQ thing bad? Well, one is that so the naive MLFQ thing is actually really bad because one, it has starvation. So once you go down your queue, you may never come up, right? And what if you do want to come up? What if like you're running a critical IO task after a bunch of CPU computation? So OS first thinks that you are a very computation heavy process. You'll just be put at the lowest priority, but then you have to run all these IO tasks when the time arrives. So the OS does not know that. It does not put you at high priority at all, and so the process just stays there, which is a bad thing. So changing nature of the thing, so that's a problem. That's starvation. Obviously there's very easy gaming of the system. You can just have a process which is running IO constantly, and then that's easy to game the system. What else was there? I think those three were the only things. Yeah. So that was multi-level feedback queue. Yeah, so these are the pros. It's a learning algorithm, so it's a good thing. It's a learning algorithm that needs a bit of time to get accurate, but can learn better for any set of long programs. Middle order between response time and turnaround time, and process is assigned a level, a priority, etc. It's just describing the algorithm. Yeah. So yeah, this is where it is. So priority boost, this avoids starvation. Every job has an allotted time at a particular level. This avoids gaming. Yeah, so this avoids starvation. At the same time, it also avoids like okay, this is just starvation in the end. So it's a starvation in gaming which you have to do. So you have to add these two things to make it more fair and more reasonable thing. Yeah, that's just an MLFQ, nothing complicated. Scheduling, relocation, dynamic relocation, and static relocation. What is relocation? I've forgotten this. Oh, okay, this is about memory management. I don't think we want to be doing this yet. But you do have segmentation. This is so one second about memory management, but we don't want to do that yet. It's the base bound. Yeah. So not yet. Free space management. To fit the segments, etc., etc. So once again, we don't want to do this yet. That's virtualization, concurrency. So you have a bunch of things over here. First, just the thread API. Create. So you know what? I'm gonna do the thing by myself. How do you create a thread? You do it using the pthread create. So you do like pthread create, pass in a function pointer, then you. What else do you do? You also have. So you get the return code for the threads ID using RC. Yeah. First, pass in the function pointer. It's the main parameter, isn't it? Yes. Oh yeah. So like you also have to create a variable which is the thread itself. So it's like you do the pthread. No, that's not this. Okay, this is not how it is going to go. So I'll just read this. So it's pthread t. Oh, you have to create a thread pointer as well. So this is what we are going to refer to. So you pass in that by reference, and then you also pass in the function pointer just by value. And this is null. So this I don't remember what this thing does, but yeah. And then you do thread A, which is the name of the thread. Fine. And then it gives you the return code. Right. Also, the return code is either like negative, the thread creation failed, or it's if I remember correctly. Right. If I remember correctly, that is. So for the process creation, it was like it's negative, the process creation fails. Yeah. So thread completion. So you just do pthread join, the thread pointer and then void star star, and what's end m? Just pthread join, right? It joins the thread. There is a pointer, etc. Interesting. How do you create a thread with arguments? Oh, okay, yeah. So this is actually for the argument. So it's thread A, right? I see. And this null thing, I don't remember it, but for something, I guess this one is always null for some reason. Okay, pthread create null thread A. This thing joins the thread. So it's just pthread join P and null. That's the thread pointer, and then you do null. Sure, that's one way to do it. You can also do pthread. Oh, this is for the return values, right? It's void star star. Yeah, it's a pointer. So m is a pointer, and then end m is the reference to that pointer. So it's the address of that pointer, and then you're converting it to void star star, which I do not know what it does, but okay. Fine, but it gets you the value basically. So when you dereference m, you can actually get the value. Fine. So just to recap, you do pthread create, you pass in the thread variables. It's like pthread t. That's how you define a thread variable. You pass in a null. Just I don't know why, but you do. I don't know what that one option does, but okay. And then you pass in the function pointer. So it's okay. And then you pass in the argument. So it's arg star. So you're gonna pass in like I don't know, whatever argument you have. Here it was like a string or something, that's why. Okay, and then to do a thread joining, you just do pthread. Yeah, just pthread, that's the module of this, right? So pthread join, and then the, yeah, and sometimes you don't have that, so it's like, okay, so the process, the thread variable, and then to get a return, you have to pass in that thing, right? So this gets the return. So it's like int star, caret star, etc. Fine. Thread completion, creating a lock. So this is something I remember. So it's like just so you have pthread mutex t, and then you get the lock name. That's I define a lock variable. Whenever you want to lock the thing, all you use like, so with capital P, so it's like pthread mutex lock, and then the lock variable. So it's like passed in as a reference, and there you go, that locks the thing. And when you want to unlock, it's just unlock. So creating a lock is just that. So you just do lock, and then you unlock. Critical section over there. Fine. So you'll also do this pthread mutex initializer, but most of the times you do not like explicitly do this thing, it's just there, but yeah, you can do this as well. Similarly, for condition variables, you have a pthread condition initializer. So you just do, first you create the object, it's like pthread conditions, it's like a COND T, and then you do, so whenever you want to signal, it's like pthread signal. Yeah, and when you want to wait, it's like pthread wait. So for waiting, you also have to pass in a mutex. It's like you pass in the reference to the condition variable, and you also pass in mutex reference. So wait is like condition variable, and the lock, and signal is just condition. If no thread waiting, this just goes to waste. Yeah. Alright, that's thread API, which lets us do all sorts of crazy things. So first we're just going to do locks and condition variables, and then finally there's semaphores. So I've read semaphores finally, and yeah, I can tell you what they do. Fine. So it was a solution for 2 threads. It's pretty doable. Yeah, right. So you have a flag which is like a list of two, so it's like binary variables, it's a bit array of two, so it's 0 1. Okay, cool. So for a thread, when it wants to do its own thing, what it will do is, first it will assert that it wants to do something, so it's like it will set the flag to 1, right? Then it will try to give the turn, so there's a turn variable which tells you which turn, whose turn it is. So it will set the turn to somebody else, right? So this is going to be deterministic, and that's a good thing. So it's trying to give away its turn. So it will give away its turn, right? Now if somebody else also does like no you, no you, no you, and then eventually you have somebody speaking, right? So you do that, and then you get, so after this thing, you'll eventually have some value for the turn variable, right? It's either 0 1 depending on which thread last did this give away turn thing. Then what it will do is, so while while this is like somebody else's turn, and then they also have the intent to do it, it's going to wait, right? So okay, while it's somebody else's turn, or they have the, I think that's how it was. No, okay, so they also have to have the, so they have to have the intent, and it also has to be somebody else. So there's an and condition. So if it's somebody else's turn but they do not have the intent, it's like okay, fine, I'll do it. So while turn is not its own turn and it's somebody else's intent, right? So the intent of the other guy is 1, right? It will wait. So it will just be like pthread condition wait, and you just wait. So it's like you put the condition variable, and then you also do the, oh wait, okay, you don't use the condition variable yet, so you can just do a yield. So to put in a waiting state instead of doing a spin waiting, but even spin waiting is fine. So just do waiting, right? So you're gonna wait that. So it's like while that happens, you wait. Then after that, yeah, shit, what happens after that? So it has to be a if condition, if like, let's not do the thing. Something is weird. If I remember correctly, it just does whatever it wants to after that point, right? Yeah. Still, I'm going to see what's going on. Okay, so it spin waits, sure. I see. So it just does a lock thing. Okay, then it can do whatever it wants. So then it does its own execution thing, and yeah, so if it's gonna do its own execution thing, what that implies is that the other guy did not show intent, and it's not that guy's turn. Okay, or it's not that guy's turn, right? And then it's just continues with the thing. So since it's now showing intent, and it's also this thing's turn, right? Since if it's not the other person's turn, it's your turn. So you are doing the thing by showing intent, and you also have a turn. So the other guy will like keep on waiting. So it does all of that stuff, and then it does an unlock. So unlock is literally just, you just like set the flag to 0. So now you do not show the intent. And so the other guy, so the turn is the same. So like, but okay, the other guy is like, okay, you do not show the intent, and the turn is yours, right? So I'll still do whatever I want to, because although it's your turn, you're not showing intent. So the other guy will keep on doing its own thing, and so both of them work as if they're like sequential programs, right? It does not run, although it's like there could have been a context switch at any time. Fine. So the thing is, you can remove this spin waiting, you can just have a yield, so it just gives up the thing, right? So this doesn't use any atomic instructions or a hardware, so you could use the yield, but fine, you don't want to. That's Peterson's solution. So this is obviously having the problem that it only works for 2 threads, because the fact that the other, so you gave away your turn, it's like if it's not another person's turn, it's your turn. If it's not your turn, it's other person's turn. This only works for 2 people, because as long as as soon as there are 3 people, if it's not your turn, you do not know whose turn is it, and if it's not somebody else's turn, you don't know for sure that it's your turn. It's a messed up scenario over there, right? And like there could be multiple people showing intent, and then the turn is like somebody's. It's, it's not yours. Okay, fine. Okay. So you're gonna wait till any one of them is having a turn, right? It's kind of a messed up scenario. So this only works for 2 threads. So test and set. So it's pretty easy. Test and set is just like a atomic instruction. So this only works, by the way, when you have load store architectures like MIPS, for example. It has a load store architecture which is like running atomic instructions. So this can work for that, but it won't work for something like x86, which does not have that. So like most modern computers, it won't work. So Peterson's solution is although good and a classic, it's not usable right now. So next you're going to be using the hardware to do this thing. So you have test and set. What it does is that it returns the value of the original value of a variable, of a log, in fact, of a variable. Let's just call it a variable. Of a variable, it returns that, and then it fills the variable with a new value, and it does all of this automatically, right? Yeah. So it can only be like one person who has. So it's like, and this can be used to do a lot of stuff. So it's like if you want to do a lock, you just have to make a lock variable which is either 0 or 1, depending on whether it's locked or unlocked. So if it's 0, you can lock it. And when you want to do something, you want to do a lock, all you have to do is like while lock. So like while test and set lock 1, a lock variable, and 1, if that is equal to 0, right? So if it's not equal to 1, if it's equal to 0, then that means that it was unlocked and I just locked it. So what that means is that if it was unlocked and I locked it, I need to do whatever the critical section is going to do, because now it's locked, and so nobody can do anything. So I must do the critical section, otherwise we're in trouble. And so the process goes on doing the critical section goes on to the critical section, and then it unlocks it. So unlocking is pretty easy. Just set the variable to 0. And so test and set is pretty neat. Locking is easy. Just do while test and set. Oh yeah, so it's not just an if, by the way, it's a while. So why is it a while? So how do I explain this? I don't think I can explain this. So it, by the way, takes in a pointer variable. Okay, cool. But it doesn't make any difference. I guess it does make a difference, but it doesn't. It's been waiting. It is always easy to pass in pointers by value, so it's probably a good idea. Still, why does it make a difference if it's a pointer or it's an integer? I don't know. Anyways, unlock does the thing which I told you. Now the question is, why is it doing a while? So I remember there was a reason for this, but I don't remember why. What was the reason? So if it's a if, right? So if test and set is 0, you will just oh yeah, so if it was a if, right, and your lock is already locked, what do you do? Well, do you just yield? Problem is, like, if you just yield, and then it will like pick up execution in the next program counter, which is a bad thing, because now yeah, because now you won't be like, this is going to be so bad. Just yield. Like, that's not a good idea. So you have to spin wait. You have to spin wait till the lock becomes 0, right? So it has to be a while, in fact. Cool. So instead of just spin waiting, you could also do a yield, which is probably the better thing to do, but whatever. Who am I to tell you how to save CPU cycles? Although do remember that context switching is kind of bad when it like in some circumstances, right, has an overhead associated with it. Right, so like if you are waiting for some CPU operation to get over, for some I operation to get over, and you get the result, and so just spin waiting versus yielding it could be that the spin wait is actually better, which is a weird thing, right? Yeah, it is. So in spin waiting you have the ready state, then you're gonna context switch. Sure. Okay, so for example, if there's like multiple processes, then clearly spin waiting is bad, because it could really be like, so clearly context switching could be worse than spin waiting. Yeah, when there's multiple processes. And also like Peterson's solution does not work for multiple processes. That's another thing I have to say, but yeah. Returns the old value, does this automatically, so compare and swap. It's exactly like that, except like compares with a value, and if the original value is the same as that value, it will swap, otherwise it won't swap, and in any case it returns the original value. Yeah. So this could be used for I don't know, doing something like I have no idea actually what this could be used for. I mean, it's the same as test and set, like it does the same sort of stuff, but yeah, I assume like it's more powerful, so you can probably have more constructs. So next you have an atomic instruction called loaded link, the same thing as the load word, except that must keep track of the changes to the locations that are loaded using. This I do not remember. Why did I write this? What does it do? What does it have to do with I think this is how you implement conditional variables or something, I guess. I see, this is some weird thing. So this is basically test and set, I see, or compare and swap. Only if that address wasn't modified after it was loaded. So it's something like dirty bit sort of thing, right? So if so somebody like loaded it using loaded link, and then they modified the value of the, so it's like, okay, they stored something at the location which was loaded using loaded link. So at that point store conditional won't actually store it. So it's only going to store it if it was unharmed, basically. this is kind of weird, but yeah, I could see it using like being used to do like some, I don't know, producer consumer thing. So you're gonna store condition. This is actually a consumer producer problem. It looks like that. Okay, this is basically test and set, except there is an increment rather than exchange. Exchange what? Fetch and add. Ah, I see. So it fetches the old value and it adds one to the memory location. Fine. I see. Then you have condition variables, and there's also semaphores which I have to do, but I'm not like made notes. So I'm going to do this using slides. Oh, I have not written anything about condition variables. Fine. So I can just delete this. So this is concurrent. Okay, yeah, I have to go to the slides at this point. There's no other way. I don't want to go to the book. This is very sparse and it's not going to be very nice. This is just my notes from lectures, but these are not very useful. So that's another thing. Spring waiting leads to prior to inversion. Close this. Let me drink some water first. Why is this open? Oh, because I had to open. So this must be somewhere in my books thing. Operating systems. Yeah, that's what I was talking about. So we have all the lectures over here and a few books. So we did the scheduling, we also did the processes thing, we also did the threads thing. I think it's time to go to synchronization, deadlocks, locks and conditional variables, and semaphores. So we'll start with synchronization. Right, so this was done on 23 I don't remember it again, but let's just do this thing. It's lecture 5. Right, so this is lecture 5 and this is going to be lecture 6. Okay, cool, we're in the correct order. Let's do lecture 5. All right, so the processes, they want to communicate with each other. Why do they want to communicate with each other? I don't know, but they can. So allow information done using the signal keyword, right, in C. So allow information sharing, better performance, modularity. But what about the restriction from the prevent one process from violating another process's space when we need some mechanism to do this thing? But that's where the conditional variable thing comes in. So okay, this really should be threads, like threads which are trying to communicate with each other, but I guess this is fine. How to allow this communication? Two distinct processes, threads, but fine, because remember, if you are going to share space on the RAM, you two have to be from the same process. So here we can only assume they're doing disk operations if they are like two processes which want to share something, but we know these are two threads which are going to share something. So you have two distinct threads, a producer and a consumer. So producer is basically something which writes stuff into the buffer, consumer takes stuff from the buffer. So can we use a file? Well, okay, this is talking about processes now. Because if it's a so if it's a process, they can share file descriptors, use process storage like file to exchange data expensive if only transient communication is required, right? So if you're like only going to share one or two variables or something like that, you probably don't want to do this. You can use memory buffers. So, okay, this is another thing which they can in fact use. I kind of forgot this. So yeah, I remember this now. So even in Rust you have this thing called constant star pointers, or these things which like point to IO sort of things, so like IO places, but it's as if like they're pointing to somewhere in the RAM. So they can use that, processors can use that, the shared memory locations of the buffers to do stuff. So I guess they were, if I talk about processes, fine. So you can use a file, but that's bad because it's expensive to get the whole file just to do like a simple communication. But you can use memory buffers, which is like really nice. It's finite. This cannot assume unbounded buffers. It produces okay, if producer tries to write when buffer full, it locks when consumer tries to write. So this is cool. For processes, this is how it probably should be, but here we're going to use threads instead. So we'll use threads which share data. So this is similar to the producer constraint problem in processes, except you just have RAM as the shared resource. So threads which share data do not give consistent results. So for example, if you have multiple threads doing this thing, multiple workers, the count equal to count plus one thing is not atomic, right? So it's not like a fetch and add instruction. So what will happen is like sometimes your final counter variable will be like less than what it should be. Okay, so uncontrolled scheduling is just trying to explain stuff. The race conditions is like when you have the classic read after write dependence, but it does not go according to the dependence, right? So, or write after read, or any kind of dependency like that, which is about timing, and it becomes a race condition like that. Whether the process which was supposed to do this, or thread which was supposed to do this first, will do it first, or will it do it later. If it does it later, it's a bad problem that we have. It's a problem that you want to solve. So how do you solve this? You solve this using critical section. Well, one idea is just like okay, there's some weird stuff. There's a panic. This keyword I do not know, but fine. In Rust you have panic, but okay, whatever. So you have thread 1, so it's some computation, and then p initialized is true. So while not p initialized, q is some function. If q is not some function, p panic. Okay. So only this only happens like, okay, so if q is some function, this is run, and then after that p is some computation is run, and oh, but it does not change q. Oh, because okay, p has to be the same value in both of these ends. So if it's like p changes after that point, it's your problem. Okay, but you are doing a spin weight over here. So yeah. So I'm assuming that p initialize is currently false. So this, you can get rid of this thing only when this happens. So yeah, you'll wait till that point and then cool. So if there was a waiting over here like before this for something which was going to happen after thread 2 does all of this, it would be like a circular waiting, and that would be a deadlock. But right now you don't have a deadlock. So when threads concurrently write shared memory, program behavior is undefined, sure, without locks, that is. Thread schedule is non-deterministic, behavior changes when read on program, compiler hardware instruction reordering. Yeah, this is a problem. So there's a problem with compilers is that like they try to optimize, and then when they try to optimize, you sometimes rearrange code, and when you're going to rearrange code, you may end up doing things which are not nice for the operating system. So there's that constant push and pull which happens. So what you can do is either you can disable compiler optimizations, or you can just disable interrupts from the OS side, right, timer interrupts, or you could have locks. So multiple operations are not atomic, obviously they are not. Yeah, for example in x86 this is what you have to do, or is this xvc, I don't know. So all or none executions of an instruction executed as an event can be that no other instruction will be run in between. Right, so synchronization primitives could be, they could be condition variables, they could be logs, and they could be semaphores. Semaphores is the most popular one, which we will read eventually. So output of a concurrent program depends on the order of operations between the threads. That's critical section is something which you do not want multiple threads executing at the same time. And it's the same time, we mean like the virtualization that OS provides, that every thread is running simultaneously. That's so in that virtualization it should run at the same time. Mutual exclusion, only one thread does a particular thing at a point. Fine. Then you synchronization. So mutual exclusion is something which must be there at all times for locks, right? You should also have hold and wait, and yeah, so mutual exclusion, hold and wait. I kind of forgot this, but whatever. Oh, and no preemption. So locks cannot be preempted by the OS. That's another thing. So here's an example. Somebody's trying to, so there are like two people trying to make. So the ideal case is like when someone buys only if it's needed, and at most one person buys. But what might happen is that there's a sort of ping pong sort of thing that's happening between two people. So like if both of them have the same algorithm, they'll be like, and they do not communicate, by the way. So it's like when one person is going to the supermarket to buy milk, the other person also decides that they'll go to the supermarket to buy milk, and so now they have like two milk bottles, which like one of them is going to rot. That's the waste of resource. So you don't want to. So how can you ensure that these two people who do not talk to each other, who do not see each other, they would be able to like buy milk, like buy enough but not too much milk? So they want exactly one carton of milk from the supermarket, and once they go to the supermarket, they will buy milk and they'll come back. So we want only one of them to go to the supermarket. That's pretty much the whole objective. So you could have this stupid algorithm which is not going to work. So it's like you buy milk, you leave, and you arrive at store, you buy the milk, and you arrive home with milk. So this is a very linear sort of thing. It does not check anything. It won't work, obviously, because we did out of milk. He sees that. Person B also sees this milk. Then person A leaves for the store. Person A arrives at the store, buys milk. Person B also they both do this ping pong sort of thing, and it never works out. So it's a bad scenario over here. Okay, so you can imagine like these two running on two different CPUs entirely. Like if they were like processes, they would be running on two different CPUs. In that case, even things like Peterson solutions, they would not work. And you could put Peterson solution over here, right? It's just that the two people are not going to do it turn by turn. That okay, you will do one operation, then I'll do one operation, and so on. No, they will literally like do these things simultaneously because they're like two different people. So you can imagine that as being two different CPUs. Peterson solution does not work. What do you resort to? One is like hardware stuff, so you can have a test and set sort of thing. So your operations of like checking whether or not the other person is going to buy milk and then deciding whether or not you're going to buy milk, that's going to be all atomic, so that you do it very fast and then one go. Of course, this does not happen in reality. Like how fast you make, right? So it's pretty much not going to work that way, right? So here's another algorithm. So you could have like, okay, so now there's some taking. So what they will do is like they'll leave notes on the fridge that I'm going to go and buy milk, right? So this is exactly like Peterson solution. You show that you want to buy milk, so it's like you show your intent. This guy also show your intent. Then you give the turn to some other person, and then so here there's no turn variable over here, but you can assume there would be turn variable, right? Yeah. So I don't know, you have a switch or something for that thing, but even if you could have that, the solution won't work. work in this scenario. But here's this algorithm. It's like, if you don't have a note from the other person, so you have left a note regardless of whether or not the note from the other person is there, and you don't remove the note if the other person does not have a note, right? So if the other person has a note, we are like, okay, let's not go into this section, we'll just remove the note and we'll move on, right? Because he's already out there. If the other person has left a note, then you will say, okay, if there's no milk, I'll buy milk. So this is basically the code that you want to execute, and this is the locking mechanism outside of it. So this part is the code, this whole thing is the locking mechanism. So this is sort of like Peterson solution, where you have a flag with two values, and then they can be 0 or 1. It's like, okay, a 2 flag with 2 values, right? So this obviously does not work. In fact, you can probably see that nothing is going to work, right? Since this just doesn't work, right? Yeah. Unless you do atomic operations, nope, not gonna work. Even if you have like variables which can only take one value, not going to work, right? So the way to solve this is either resort to asymmetry. So here B is like a child. So what B is like, if there's no note from A, and if there's a note from A, it will just execute whatever they want to, and then it will like, so it just asserts its intention, and then it sees if there's a note, don't do anything. If there's no note, it will just buy milk. It won't be patient, right? So it's not caring what the other person is doing, whether or not they are checking this guy's note, or like whether after both have done this note taking, they will both go for buying milk or something like that. This guy just does this thing. But the other person, A, is cautious, so he'll say, I want to assert that I have to buy milk. So now while B is checking, right? So B is checking all the time when he has put a note. So all the while, I'll do nothing. I'll wait. I'll wait and wait and wait. And then when B is done with his checking, right? When his intention is off, either he has bought milk and then his intention is off, or he has not bought milk and his intention is off. Then I'll proceed. So till that point, do nothing. Then if there's no milk, buy milk. Remove it. And so this has one problem that so B is like this gets the job done, sure, but this is only going to be for this particular scenario where you have this if no milk buy milk sort of code. If it was anything else, right, if these two processes were having sort of different code, it would be a mess. It would be a mess, because what if like B wants to do something but it's only held back because A is showing an intention to, and A does not actually do anything, but because it has completely different code, but then B's thing is lost. There's no spin waiting for B, so it's just lost. Like the chance it had to do something, it's lost because A was too stuck on waiting. And so a while and if can guarantee this, but it's only for this particular scenario. You can't extend it in general. So this is still a bad scenario. And this is where locks come in. So you have threads, and this is basically like locks. So this is already thing they do like mutual exclusion. So mutual exclude. So around here is to add lock. So locks have two functionalities: acquire and release. A lock can be acquired by only one thread, and it can not be acquired by, so it can be acquired by the OS as well, okay? But it cannot be like preempted. Yeah. So there's safety, one lock, which is what we also call mutual exclusion. If no one is holding, acquire gets locked. What the heck? Yeah. Okay. Yeah. So if no one holds, then just right. Just hold and wait. So if you're going to get lock, everyone's going to wait till you release the lock. There's no preemption. So this is just the lock API. This is not important. The Also allocating and freeing memory. So this is the classic consumer producer problem. So you see, with just locks, this is kind of hard to do the consumer producer problem thing. So when you do a method, so okay, this is actually slightly different. So okay, how do I say this then? For memory, in fact, you have your own like heap lock sort of thing. So OS has that. OS has it. Do this stuff. So heap lock dot acquire, heap lock dot release. Yeah, so these are like system calls, sort of. It's not a system call, but there's a system call inside of it, and it doesn't look like this, by the way. These are not proper keywords. It does what it's saying, right? Similarly, free does something, but it's not what it does. Obviously, you don't see these keywords anywhere in C. But yeah, so locks for allocating and freeing memory would be something like this, that you can only allocate memory or free memory at one point, and you can't have like multiple people trying to allocate memory, right? That's just bad. And since we're all thinking of it is happening like in one address space or a process, like thread sort of. So if you're having like two mallocs running, you cannot context switch between them. Like n memory, and it's like stopping at fourth, and then the other one is like, oh, this memory ahead of the fourth one is like start allocating, and it's clashing over there. So it's not a good idea to not have critical sections for allocation and free. So this is very easy. Yeah. Goals when building locks: mutual exclusion, fairness, performance. These are the goals, but these are not the three necessities that you have. So you have mutual exclusion, you have hold and wait, and you have no preemption. These three things make or define what lock is, and these three things are something which you want to have. So you want to prevent multiple threads. That's like what a lock is. Fairness, so that's something which you have to factor in for scheduling. Performance, once again, the same thing as what we did for scheduling. So how do you implement this? Well, one thing is just disable interrupts. Yeah, don't allow context switching, but then that defeats the whole purpose of an OS. What if you have a program which is badly written, which goes into an infinite loop? Your whole program, your whole system is like going to crash at that point. You have to restart it, and this happens. This, by the way, does happen, so beware of that. So this is a problem. You'll have very inefficient running. At the same time, this doesn't work on multiple processes because it like privileged operation. Yeah. So this is what I'm trying to say is, like, if you have a critical section, only for that like particular phase you'll just disable interrupt. Don't interrupt me while I'm doing this critical section thing. And so this will be like tested and all, but this is insecure. This is inefficient as well, because you don't know whether or not you should context switch from that. Like it's some other IO operation which is completely different, wants to execute, and it's very important. You probably should execute that first, and it doesn't work on multiple processes. Peterson solution, classic, but doesn't work. So that's the first slide. Implementation synchronization. We did. Let's go to locks and conditional variables. Just something which we did from the notes. Peterson solution is classic, but it leads to starvation on one or both ends. One thing you could do is just have a yield, right? So yeah, so you don't just wait, you yield. So that would remove the starvation, but it is still the same problem that on multiprocessor system does not work. It only works if the load store architecture is there. Yeah. Test and set, the usual is like the best thing to do. This is how locks are actually done. So you have a I hate this whole, they don't use a dot syntax, they see people, but fine. So you have a struct lock. I don't know who came up with this, but fine. So this is going to initialize the lock, this is going to lock, it's going to unlock. We don't really know if you have a lock API set in place, so you don't have to do any of this. And if you want to have some sort of testing and setting, right, usage, you can just do it by yourself. You don't have to create structs and all of that. Just use normal like primitive variables. Okay, Peter's solution is classic solution, but it uses load store, which we don't have in modern day. Test and set. Okay, move on. Compare and swap is the same thing as test and swap. It can be more powerful. Right. So, for example, I don't know. What was I going to say? The producer can be easy to do. So all you have to do is like when you are a producer, right? And so let's say you are just thinking of like one variable, right? It's currently not updated, it's a null value, so you want a producer to update the variable and then a consumer to read the variable, right? So every time you read the variable, you don't want it to read again, you want instead somebody to update it and then read it, so that you get all the unique updates on that variable, right? So what a producer can do is that every time it will check, so it will be like compare and swap some flag, so it's like it'll set the dirty flag, so it's like if dirty is 1, then that memory location is updated, so you want to read that. So it will like while so you compare and so you get it's like compare and swap, so it will say if your dirty was 0, will make it 1, so it's like while compare and swap dirty, so you have to pass in a pointer an expected value which will be 0, so it's just 0, the new value will be 1, right? So you do that, you get the previous value from this. So the previous value was 0, then you must have replaced it by this atomic instruction at this point, right? And so now you have to execute whatever you have to execute. So you have acquired a lock sort of thing basically, right? So no person is going to be like running it after that, because so all the consumers, so all the producers are having like a 1, they see the variable is 1, so the only way you could make it 0 is if somebody else did it, right? So you could use this. Similarly for a consumer, you just have to like compare and swap the pointer value itself. The expected value should be 1 and then the replaced value is 1. So while compare and swap for that is equal to 0. So if it's 0, then it's a problem, so it will wait while that's true, and if it's not true, you'll execute whatever you want to execute. So you can have an easy locking mechanism set in place. Now there is a problem that multiple of these things could be like activated at the same time, right? So you have a producer, then so a producer does the compare and swap stuff, and so now he's active, but then another consumer comes in and see, oh, you have done the compare and swap stuff, so he just assumes that you have done the code thing, and so he becomes active, and then that makes another producer active, and then another. So it's a problem. So you need yet another lock, which is going to lock, which is like going to only make one person do something at a time. So this one avoids like a producer acquiring a lock and then getting stuck, or a consumer acquiring a lock and then getting stuck, right? So the whole conditional signal variable thing that is avoided at that point. But it also does not fall into the problem of that they are not mutually excluded, that like multiple of them are active at the same time, because if multiple of them are active, then you would face the same problems, race conditions, which is bad. Okay, so this is cons of spin waiting locks. You can just use a yield pro. Oh yeah, so this was an example. So this is a Mars rover, and they had some performance issues because of this locking mechanism being bad or something. So yield is what we should use. So this is how a lock should properly work, not using spin baiting. So a pretty simple fix, in fact. So now you have the producer consumer problem. Fine. So this is where things start getting weird. So you have all of this API, but we don't really need any of it. We just want the code finally. Yeah. Mesa semantics. Okay, we don't need any of this, the problems stuff. So you have a producer, you have a consumer, and so here's what they're doing currently. You'll lock the thing, and then so the compare and swap stuff that I was talking about, you can use the same thing using a conditional variable. So you have just one conditional variable, so it's like, and then you have a count, which is like the buffer sort of thing. So its count is 1, then the buffer is filled. If it's 0, it's not, right? So what a producer does is that if count is 1, right, then it's gonna wait. So it will wait till the count is 0. So it is a pre-thread condition wait, condition, then the mutex. So here's what condition wait does. It puts it into the waiting list, right? It puts it in the waiting list, waiting for the condition signal, in fact. Right, so you have a list for conditional variables. Every conditional variable has a list, right, which is like a waiting list. Okay, so you do that, but at the same time, you also free the mutex while you are waiting. So once you're going to be put out of the waiting list, you will get the mutex back immediately. But right now you're going to free the mutex, right? Yeah. Okay, I'm saying you're going to get the mutex back immediately. You're not just going to be granted it if somebody else also has the mutex. Because if somebody else has it, then you're going to pretty much wait for the mutex, right? So although now you're out of the waiting list, now you're in the waiting list for the mutex. So it takes you from waiting list for the conditional signal to now the mutex. So it's like you're a step behind, and now you're one step ahead, just something like that. So it's basically like this. Somebody comes up like, I'm going to produce, so lock everything down, nobody else should come to my like cabin or whatever. Then they say, oh, count is 1, somebody has already produced. So it's like, then I don't need to produce. So if count is 1, I'm gonna wait till somebody uses whatever I produced. So it's just like a p-thread condition wait, and then it waits for the signal, right? And so like it just sits out of it his cabin or whatever. Assume just one cabin basically. It's like one cabin, and then there's all the tools in that cabin, and only one person can produce something. When something's produced, it has to be consumed. So I don't know what I'm talking about, but you can probably understand that. Okay, so this guy just comes out of his cabin, and now he's like that I'm gonna wait till somebody else comes up. So it does a condition wait. It also frees the mutex. Now he's not locked the cabin because he has to come out of the cabin, so he has to unlock the cabin, right? Comes out, unlocks the cabin, all that stuff, and so he waits. When somebody else comes in, he does consumption stuff. Once again, he logs, consumes, and goes out, right? So count is 0, by the way. It is 1. Sorry, count is not 1, by the way. Count is, oh sorry, count is not 0, count is 1. He will not do this waiting stuff. So he just does whatever he has to. He consumes it, and then he goes out. So while he's going out, he also makes a signal, and this signal which this guy will pick up on, and then he'll continue the production thing, right? So every time you're done, you signal the other party. Yeah. Now here's the problem, that your signal is the same for both producers and consumers. So if a producer is trying to tell a consumer that I'm done, it can even feel to some other producers that, oh, he's done with the consumption, and that's a problem. It's a very big problem. Like, imagine if like a male I don't know, a male deer was to give off signals, and then instead of all females coming, all the males came. That would be very weird, and that would lead to extinction. You get the thing, right? That it's not going to work. So instead, oh, that's not actually a good idea. I mean, males, females. It does work like that, doesn't it? Let's not get into that. But yeah, so you do a signaling to the other party. So you require two conditional variables, obviously. And so yeah, okay, you still don't have two conditional variables. Oh, come on, where is it? Okay, right, now you have two conditional variables. So you have an empty and you have a filled, right? Or you could just have like a signaling to the producer or consumer. It doesn't matter, you just have two conditional variables, C1, C2, even that works fine. The naming does not really matter. Right, so once again, this guy pretty much does the same thing. That okay, now this guy is a bit more complicated. So instead of just doing it once, he actually wants to do it multiple times. I don't know. So every time he'll be like, lock down the cabin, I want to do it, right? So he tries to lock it down, but then if it's already locked down, well, what can you really do? So if it's not locked down, he'll be like, lock it down, no one's inside. I go in, I see what's in the cabin. If there's already produced over there, I'm not needed, I can't produce. So I'm like, wait for the signal till it's done, and at the same time also unlock the cabin so that you can go out, right? So remember, at this point the cabin is locked, no one else is like able to see what's going on in the cabin, so no other thread is going to be able to execute the critical section. Yeah, this guy has acquired lock. So what he does is he unlocks the cabin and he waits for the signal at the same time. Fine. So its count is 1 and he hasn't done anything to the count. A consumer comes in, he will do something to the count. So for him everything works out perfectly. He signals the empty condition variable, which is what this guy is waiting for. He's waiting on empty. So he waits on empty. He's like, okay, this is empty, cool. So now I'll try to get the lock. So maybe this guy like signaled way from inside or something, I don't know. So he did something, he signaled it, he went outside. Maybe there was somebody else who grabbed the opportunity and just went inside. We have no idea, but that happened. So either this guy finds like an empty cabin, it just without any produce, and then he can continue, or he finds somebody already in the cabin. So it could be a consumer, it could be a producer. Of course, it won't be a consumer just after a consumer, because it's just not going to happen. You have a consumer doing something, you set the count to 0 before you ever let anyone else do anything. So you do the count equal to 0 thing when you do the get, and count equal to count equal to 0 thing, do the get, and then you unlock your mutex. So anyone else can't do anything. So when this guy tries to do something, it's going to be 0, right? The count is going to be 0 if it's just after that consumer. And so this works out, right? So remember, you have these while conditions over here. So it's like while count equal to 1, p thread condition wait. So what this means is like, except that some consumer like did in fact signal and everyone heard the signal, so all of them are like free now. Okay, in reality that does not happen, since the OS does not want to do too much. It just like signal only goes to one person, right? But yeah, so it could be like you have multiple processors going on over there, right? So multi-processing. So in that case, like, I don't know, 2 consumers are working at the same time, there are 2 cabins, I don't know, and then both of them signal. So like, so now you have like 2 producers in fact. Okay, if you have 2 consumers, then the mutex thing is also automatic. You would need a semaphore for that. That's much more complicated. Not cool. why do you have a while then? Shouldn't just a if suffice? So if count is 1, then you do that. Think about it. Why do you have a while instead of an if? I mean, I get that with semaphores you would probably have a while, but still, you would have to check again and again. Think about it. Look, so if this guy is signaled, it can only be signaled through a consumer. So it's just impossible that you would have. Yeah, true. So why do you have something like that? It can't be that the signal will like free everyone, right? Like everyone will try to get the mutex. I don't think that's gonna happen. Yeah, I don't think that's gonna happen. Is it gonna happen? I think I should search this. So how do condition variables actually work? Why do you require the while? Why is there a while in producer consumer? Problem with condition variables. Okay. Sort of broadcast. What the heck is this? I mean, obviously we are doing pthread condition signal. Okay, this isn't very much working. Oh, this is exactly the same ping pong. Yeah. So, I see. So this while is reminiscent of semaphores. So here you just have count equal to 0 or 1. But what if you did have like multiple sheds or multiple cabins? Then that would be a problem, because then your so the thing is like while count is less than. Yeah, okay, this makes perfect sense somehow. Yeah. But it's like negative, you cannot do anything. Sure. So like, yeah, because if some consumer signaled you, but then I see. It's messed up, isn't it? Yeah, it is. So you have like multiple producers waiting, and then a consumer comes in. He's like, okay, cool, I'll consume. So yeah, I get it. It has, you have to wait for semaphores to understand what's going on. Okay, if using a single condition variable, should use notify all to wake up all waiting threads in order to avoid waking up the wrong thread. What the heck is this? So does this wake up all the threads? Does pthread condition signal wake up all threads? At least one of the threads that are blocked on the specific condition variable. Okay, in the order in which they are unlocked, sure. Oh. I see. That's a problem, isn't it? Because if there's a if and multiple threads are woken up at the same time, that's the massive problem. Oh, I see. Yeah. Not good. Definitely not good. Multiple resources over there. The resource allocation now. I see. Because if both of them put it in the same slot, that's a problem. So you only want one of them to be doing the thing at one time. Yeah, but okay, but the put thing has to be. This is kind of complicated, isn't it? Sure. It's multiple processors, or that's going to be a problem. It could wake up more than one thread. I see. That's the whole problem, because if there's multiple threads doing the same thing, they're going to cause mayhem, right? Because if it's just a if, right? So if this thing was a if instead of a while, then what's going to happen is you have two producers for waiting. There's one consumer who gives a signal, then two of them wake. And two of them wake, they don't look like what the count is. They don't worry because they were in the condition wait thing anyway, so that is passed to them, the checking thing. And then they just simply just put, both of them put, which is a problem. You don't want both of them putting at the same time, right? Okay, it's not the same time, they still have the mutex thing, so it's like one of them will put, then he'll signal and all that, and then the other one will put. But the problem is that the other one will also generate a signal and all that, and yeah, it's a messed up scenario. You do not want two of them working at the same time, so that's why you require a while. So you can have spurious wake-ups, spurious, whatever. So condition variables, they hold log going on. Okay, memory less. Yeah. Right. So here's the good thing. Either you will have count equal to 0, right? So and some producer who is yet to come and produce, right? And that will happen, in which case it's completely fine to wait. Or you have count equal to 1. So you can't have a situation where a consumer is just stuck, pretty much, right? Like its count is 1 but it's waiting, and that would be weird. So yeah. Memoryless. There's no lost signals. I mean, there could be lost signals in terms of the conditional signals, but it would either be changing the count or signaling somebody, right? Yeah. So wait happens in the loop. Fine. So this must thing is not explained why this happens in the loop, but okay, it's kind of clear now. So woken thread may not run immediately. Signal plus thread on the ready list. Anyone can acquire it after release. Yeah, on the ready list and acquire it. Acquire what? Acquire a CPU. It's in the ready list for the mutex, by the way. Yeah. So this is interesting. So you can think of the mutex as like being its own sort of CPU thing. So each process has 3 states. It's either waiting because the conditional signal, right? So it's like waiting for the conditional signal. Either it's in the ready state, so now it's like waiting for the mutex to be assigned to it, or it's actually running. So then it will be like when it ends or when it goes into waiting state once again, it leaves the mutex. Cool. That's pretty sweet actually. And then you have semaphores, which, so this is what they use for like aeroplanes, right? So this is what semaphores are in real life, but here they're just like, they're exactly like locks and conditional variables. They're just synchronization primitives. So what they do is like whenever somebody wants, so whenever a wait is called on a semaphore, it will decrement the value of the semaphore, right? And if it turns out to be negative, the value turns out to be negative, then it will be put into a waiting state, right? The process will be put into the waiting state for the semaphore, right? So it's a bit like conditional variable because it has its own waiting state. So do logs, by the way. Yeah, even they do, but like there's no signaling and all that, right? So it's a bit like conditional variable. So like whenever you signal, you put something from the waiting state to a running state, right? So I'm saying a running state and not a ready state because yeah, if you're going to signal something, then that means you have a slot ready for them, so they can just straight up start running, right? Yeah, so you can only increment and decrement the value. There's nothing else that you can do. You can signal. So when you signal, you increment the value. At the same time, you also put something from the waiting list to running if it was negative before. So how negative it was is basically like how many threads or processes are like waiting. Okay, no processes, but threads are waiting, right, for a signal. So this like pretty much makes our whole job easy, because now instead of using so here you just use pthread condition wait, right? But over here it's like pthread condition, yeah. So it's gonna be like while, so you don't have to do this whole how do I even say this thing? So it is in fact this is extremely weird. How do I even say this thing? You don't have to do the count equal to 1, pretty much. You can straight up just start with the wait. You just straight up say pthread condition wait. Don't do the while thing, because it's guaranteed that when you signal, it's either like one of them is going to be woken up or you're releasing a resource, so its value will be incremented. So it's not like anything is lost at this point, right? Yeah. All right, so this is the value is increasing the same or down. Signal wait impose deliberate constraints to avoid errors, often clean and organized, implemented efficiently in many systems. So this is some weird random rules they have. Guarantee that A1 happens before B2 and B1 happens before A1. A1 happens before B2, yeah, and B1 happens before A2. So this is not related to semaphores or anything. You could do it however you want to, right? So if I had to do this, I would do this using conditional variables. So it's like after A1 you conditional signal to some B2, right? Yeah, and till that point it's like it's waiting. Okay, that's actually going to be a problem, because if the signal occurs first and then the wait, then that's a problem, right? So you have another counter there. That's one thing you can do. You could also do it with logs, I think. So it's like you give away the log to A1 initially. Yeah. Okay, I think logs is fine. So you can have two logs. Let's call it L1 and L2. So before A1 you just do L1 acquire, and then after A1 you do L1 release. And before A2 you do L2 acquire and then L2 release. Over here for B2 you will have L1 acquire and L1 release. So what's going to happen is B2 can only run if A1 has run. Similarly, A2 can only run if B1 has run, and that's perfect. That's what we wanted, right? You can switch between A1 and B2 like without any worries. You can execute stuff because they use different logs. So that you can switch between A2 and B2, but you can't like switch between A1 and B2 at your mercy, at your will. So it accomplishes the thing. So it's just logs, simple logs. So this is fine. There's no problem in this, except there could be a problem, right? So there would be a problem if you had wait, I think I'm missing something. lock dot acquire. Oh, okay. So you release the lock over there. So can it be that A2 runs before B1? If A2 runs before B1, then that means it acquired the lock before that. But that means A1 has run before it, which is fine, which can happen. I see. Huh. Well, that's bad. A1 and then A2, and then you have B1. What the heck? No. You want B1 to run first. Yeah, you want to acquire that. Well, this isn't really helping. Here's another thing you could do. You could just be like that, you know what, scrap this, scrap locks and all. I'm just going to do spin weight at this point. So you could just have two variables, L1, L2. So I'll just set both of them to be like 1 since they're like acquired. Alright, so what B1 will do is it will set L2 to 0 and A1 will set L1 to 0, and B2 requires L1 to be 0, and then it will run, right? So it will just have a spin weight basically. So only time that your L1 is 0 is when A1 executes completely. Fine, and that does it. That does the whole thing. So what sort of structure was this? Is this a lock or what? Well, you initialize it or something, then you didn't release or anything, you did decrement it. Okay. Huh. I see, you increment thing actually, so you released it and then you decrement the thing. Oh, this is basically semaphores which I did. I see. Could it be conditional variables? No, it's not conditional variables because signals are lost. Over here signals are not lost, so it is in fact semaphores which I did. I see. Semaphores are extremely easy apparently to implement. So I did semaphores, fine. Could I have done this with locks? Sure, if you could initialize it as you know, locked. Can you initialize a lock as a locked thing? Well, I guess you probably can. I don't know. Anyway, I'm just gonna move on. So to deadlocks. So this is a whole different topic, and this is going to be in the next slide, like the next bunch of slides. So we won't do this right now. Okay, so multiplex is, by the way, just multiple exclusion. So this generalizes the previous solution, so that allows multiple threads to this is just semaphores basically, right? So this is deadlocks, semaphore usage. Yeah, this is usage. So binary semaphores is just a lock basically, except these are like locks which can start with positive values, which can start with negative values. Yeah. So if like you initialize semaphore with -1, it's like for somebody to start execution it has to be 0, so somebody has to release the lock. So it's like somebody's acquired it, I don't know who acquired it, something like that. So it could have its own use. It's basically like a lock which starts as locked, which is a messed up thing, but that's just how it is. So you could just give it to somebody, right, and they do not have to execute a command so that this happens. You just initialize it like that, right? So like before creation of these two threads you could be doing that. Of course semaphores work perfect because clearly they do still, right? Yeah, that's what I'm talking about. So counting semaphores are like conditional variables, whereas binary semaphores are like locks. Except that counting semaphores are not exactly conditional variables. You could have you know, storage, which you do not usually have in conditional variables. Yeah, like if a signal is lost, it's lost. For a semaphore instead, if a signal is lost, well, it shows, it changes the value of something. So okay, you can initialize semaphore with -1 as well, which is a good thing, because then you could solve this problem very easily. Just initialize two semaphores with both -1 values, and then after A1 you release the first semaphore. So you signal it, and then you wait on it just before B2. And there you go, you have your execution correct, right? That's cool. And yeah, this is basically like how you do producer consumer in semaphores. So this is basically like a semaphore of multiple bits over there. It's a multi-size, multi-element resource. Okay. So just as before, you have two conditional variables, except that here the thing is that the mutual are inside, which is weird. But the get and put are put inside. I wonder what would have happened if the mutual were outside. Then you would like wait for the item. Oh yeah, because semaphores not release mutations when you wait. That's the problem, right? So you require them to be inside. Yeah, so this is a classic thing where you could be having a deadlock, except that your starting values are such that you can never have a deadlock, right? So your items and spaces both are like this. So it's starting with 0, and this is starting with a buffer size. So it's like all empty. So you will just do persist.wait, which will decrement. So I'm assuming this is actually a consumer and this is a producer, because it's waiting for spaces first. This is waits for spaces. Yeah, because it does a put as well, so obviously. And then it wants to acquire the mutex so that it can run in a critical section. Then it does the item sort signal. Sure. Wait, why does it do item sort signal? It does spaces dot wait. Okay. Yeah, that's fine. So every time you run one of these fully, the spaces gets decremented by 1 and item gets incremented by 1. And so spaces plus item is in fact going to be a fixed number. And so program, like in a programmer logic way, you could be thinking that you just need one variable to do all of this, but you need two semaphores to be doing all of this. So two different ways to lock the thing. Yeah, that's fine. That's fine. Because then again the same problem would happen, that if it's a single semaphore thing, then the signal thing is just going to, yeah, that's the problem, isn't it? It is. So both of them would have signals, which is bad. And then you want the wait command to work the way it does. So yeah, so that's for producer consumer. Fine. So you got that. Locks is done. So you also have a whole thing on semaphore. You have a thing on deadlocks. So let's see which of them is the next lecture 6 the same? What? Wait, what? Wait, that doesn't make any sense. This is lecture 6, so how is this thing? It's the same as before, isn't it? Okay. Oh no, it's different. It's different. Fine. So we did this and then we did this as well. Okay, so what is generalized video solution that allows multiple threads to run in critical section at the same time but no more than n threads? That's exactly using semaphores, right? So your mutex was like, okay, so your mutex was just, you know, a semaphore with what, with 1 basically, right? So here you could just have mutex with n. It's like a number of instances that you have. Fine. No, this is slightly different from, I see, because there's no mutex apparently. So, oh, but if there's no mutex, then that's going to be a problem, right? Because yeah, I don't think this is correct. Or you could just make get and put to be atomic. Yeah, that's the problem, right? So if you have like two things putting at the same time, because currently it's all spaces, right? Yeah, so if you have two things putting at the same time, they both do a spaces dot wait, fine, then they do a buffer dot put. The problem is like put is not atomic, so what could happen is you get the same value. Okay, so okay, you have some value, fine, you're putting I, whatever, your fill value is the same, so it's 0 for both of them, and they both are occurring simultaneously. So it's like first one executes this one, other one executes this one. This is a big problem which should not happen, so that's why you require the mutex. Yeah, that's easy. Then you have the dynamic philosopher's problem. So this is what a philosopher does. So forever it just thinks, it gets forks, eats, and it put forks, right? That's what a philosopher does. Yeah, so there could be a deadlock over here, because it's like, so one philosopher is trying to get the forks, but like, okay, everyone has the left fork, yeah, so the fork to the left, and so nobody can get both the forks and eat, which is a problem, because now nobody gets to eat, right? So they'll just get the fork all simultaneously, they'll try to eat, they cannot, they'll put the fork down. So it's a problem. So what we need to do is just somehow figure out a way so that everyone can make some progress. So that's where like a buffer comes in. So this is like whether or not a fork is up is basically like a condition, right? So you could either have like 5, I think, yeah. You should not have 5 locks, because once again the same problem occurs, that you have left and left and left, and all of them get left one. problem. Or you could just have one mutex. It's like the person who gets to eat is just one. There's only one person who gets to eat at a time. Yeah. But what's your solution? So you have a left, right. So given a philosopher, you can get the left spoon and the right spoon. Fork, sorry. And so here's what we do when we get forks. So we have a semaphore, sure, and we sema down it or wait for it. Yeah. So we wait for fork left and for fork right. And then while we're putting forks down, we signal the left fork and we signal the right fork. That's kind of bad, isn't it? Wait, what? This is something that you use with a semaphore. So you're saying this is a semaphore. Forks left P, that's a semaphore. That's a bad situation. It leads to deadlocks. Yeah, okay, that's what we are looking for. Yeah, it will lead to deadlocks. One way to do this is like you just give one philosopher the chance to eat at one time. So he eats, he puts it down, and then somebody else gets the chance. So the chance itself is something like a resource that they're going to have. So that's what a deadlock is. Mutual exclusion. So I thought this was about semaphores. Why did it become deadlocks of all things? Okay. Preemption, circular rate, usual. So we still do not know how to actually build semaphores, huh? Dumber. Right, and then it's all about deadlocks, like how do you reduce deadlocks and stuff like that. So there's only three things you can do. You can do prevention, you can do retracing back, and then you can build systems where this happens. Okay, that's actually prevention. So just two things that you can do. So yeah. So just as we saw in the dining philosopher problem, if everybody has like the left fork, then nobody gets to eat because all of them are like waiting for the right fork, but there's no right fork. Right, the usual. So you can do prevention, you can do recovery, or you could do avoidance, which is like ignoring it completely. Oh, so, okay, avoidance is not that. Avoidance is like, it's also actually prevention, fine. Make it impossible to have deadlocks. So they say make it impossible, but really they're just figuring out when you have a deadlock. So this is called a resource allocation graph. So basically like every resource is a node with multiple elements inside of it, I don't know, and then you have a requesting edge and you have a claim edge. So a claim edge is basically like the resource is allocated to this process, and the requesting one is like this process wants to get this resource, it's waiting for it. So all of these resources can be modeled using semaphores, pretty easy, right? So at any given time, like if you have a situation like this, that this one is requesting this, but this one is giving to P3, which is requesting this, but this one is giving to P1, right? And that's kind of a deadlock, except this one is not really a deadlock because your P2, P4 will execute at some point, and so then this requesting edge will get R1's resource. Similarly, this requesting edge will get R2's resource, the other instance of the resource, right? So the graph contains no cycles, there's no deadlock because everything's linear and everything is like, it's a tree basically, so it's like it will all go back, it will all be done. Here we're assuming that all processes run, like all processes halt obviously, but that's fine, that's okay to assume. Like all processes will give up the resource at some point, that's what we're assuming. So if the graph does contain a cycle, then only one instance per resource type, then definitely deadlock. Instances per resource type, possibly still have deadlock. It does not actually say exactly when do you have a deadlock, but it does tell us when you do not have a deadlock. So this is when you don't have cycles. But as we just saw, having cycles does not mean that it is necessarily going to be a deadlock. So these two are necessary because visual exclusion is the whole point of a mutex, so must hold for only non-shareable resources, and hold and wait is also necessary because otherwise, yeah, it like, I mean, that's how a lock works. It's not hold any other resource. Right, so this is like something which is not really avoidance. It's like when you get a new process, right, and it's requesting stuff, then you figure out whether or not that's going to lead to a deadlock. And so you do not run that process yet. You let the thing complete and then you run it. Alright, so this is so now we are going to an algorithm to actually solve this problem, which gives you like a sequence of how to run the program so that you never run into a deadlock, which is also called like a safe execution order or something. But yeah, so here what we're going to use is something like the maximum number of and different type of resources that you would require, which you get at the compile time, right? And then you dynamically examine the resource allocation state to ensure that there can never be circular wait condition. So for example, so this is a safe state. The system is a safe state if there is a sequence such that if you run these processes in this sequence, the system will still be that safe state. It will still be like in a consistent state. Right? There would not be a deadlock. Yeah. So avoidance ensures that a system will never enter an unsafe state. So if it's going to happen that it's like you compiled a bunch of programs and then you set up the threads and you just figured out after compilation that, oh, this is a bad scenario, you can never have a safe execution order for these programs, then you're obviously going to end up in deadlocks, right? I mean, there's a very high possibility that you will. So what you do, and you do not want to run into deadlocks, so what you do is, and this is by the way, like assuming that you already have some processes running, so you only have some resource available for you. So this is in very tight conditions that you're going to run. Even the processes themselves might have already like been like started to run, and then some of them have got resources, and now you are figuring it out in an unsafe state. So there's a possibility, right? So the only way you can do this is like basically not let one of these processes run. If there is an application or something, you do not let that run. So this system will never enter an unsafe state. Yeah. So if there's a single instance of a resource type, you can just use a resource allocation graph, right? So that's something like this. Yeah. And in such a scenario, it's kind of obvious that if you have a cycle with just like single instance every time, in that case, if you have a cycle, then you are in a deadlock. So you can only add processes which do not cause more cycles, pretty much. Now here's the weird part. Suppose your graph did not have any cycles till now, and you have a new process which is going to request, right? It's going to request to all of these resources that I want an instance of a resource. You can still never get a cycle. Yeah, which is a problematic thing, because like let's say you have a process P5 and it's going to request both of these Well, whatever cycles there were previously, they all stay, but from this guy you cannot have cycles, right? Yeah, that's because this there's no way to reach this process which has just arrived, so you can look at it if yeah, something like that. Of course, this graph changes with time, so it's just when you add a process you do not know for sure whether or not this is actually going to lead to a deadlock, but at some point, right, if you are going to allocate a resource, it may lead to something like a deadlock, so you can be very that using this allocation graph. Figures out whether or not you have a resource allocation problem. But this bankers algorithm thing actually figures out whether or not you could be having a problem. Yeah, I mean it's not in the deadlock stage yet, but you could be. Wait a second. No, wait, I said it wrong. Oh, you are in the deadlock stage because yeah, even if you like give every process all the resources that you have, you can still never do it. That's a bummer. Unless like the processes are decomposing into a bunch of processes which you can actually run one by one, and then it's gonna work out. But oh yeah, so this is going to give you a very high probability of it not working out. Yeah, even if you like started with all the resources that you have, it may not work out. Let's see. So this can only do like you can figure out whether or not it is a problem. So this is a claim sort of. Okay, this is I think a request edge. Oh, okay, this is a claim edge, so it requests. Yeah, fine. So this is like a proper request that the process 2 requires some sort of a resource R1, but this is like it may require R2, right? So if your graph is like this, that you figure out, okay, the process 1 may require R2, and currently this sort of stuff is going on, right? So unless like process 2, so unless process 1 gives up R1 somehow, right, before R2, this is going to be a problem because it's going to be causing a deadlock. So this is where you do avoidance of deadlocks. Fine. That, yeah. Yeah, it does not result in the formation of a cycle. So you don't. So like initially, you just start everything with all the edges properly assigned as it should be. You do not care about deadlocks at all, and then you start assigning edges, but you only assign it such that you may not run into deadlocks. Okay. Return them in a finite. So these are the assumptions it makes. When a process requests a resource, it may have to wait. Sure. Each process must claim maximum usage as the beginning. Multiple instances. When a process gets all its resource, it must return them in a finite. So basically, every process halts. That's what they are trying to say. Use different data structures to enforce this. Max matrix, allocation matrix, need matrix, available list. So this is a max matrix, so it's like the maximum number of resources that you have. So A is a type of resource, B is a type of resource, C is a type of resource, and these are the processes. This is the allocation matrix right now, and so the available is just this thing, right? So this is how much they would require in complete execution. This is how much they have been allocated yet, and this is how much is available. So three of them are pretty obvious. It's just available list, max matrix, allocation matrix, and then there's a need matrix, right? So need matrix is just like max minus allocation. And so yeah, there exists a sequence P. So this is pretty easy to figure out. Okay, first just the need matrix. So this is very easy to figure out. This is like P0 currently needs 743, P1 needs 122, P2 needs 600, P3 needs 011, which is very easily available. So it's like 332 easily. You can just give it to that, and then whatever it currently has, so it's 211 allocated to it. You just add it back to the available resources because it completed, right? So it's just 5, 4, 3, and then you can easily execute this one and then get back. So it's just 6, 6 and 5, and then you can run this one and that one, and it works out. Sorry, I meant like, I mean, it's fine. You just get like 10 at that point, so it's very much doable. Right? You give it the 4, and then sorry, you're not supposed to add the 1 to 2, you're supposed to add the 2 0 0, but you get the thing, right? So whatever is allocated you get back. That's a pretty simple algorithm. So if there exists a sequence, then you know for sure that there is a way that you can convert these claim edges to actual like request edges, so that this would be fine, this would work fine. So if there's a cycle that exists, so it's just periodic. Okay. Yeah, so I mean, you got it that it's a deadlock, but that does not really help, does it? Sure. So you have a graph like this. Okay, so Pi to Pj, that's like if Pi is waiting for Pj, so Pj should release whatever resource he has. Yeah, it might be that some process is like waiting for multiple processes or something like that. Fine. And then like multiple processes waiting for a particular process or something like that. So then whenever you like, let's say like P3, so P2 is waiting for P3 and P3 is waiting for P4, it's waiting for P1. Okay, suppose P5 executes, right? Then P2 is waiting for, okay, this is a bad deadlock because there's clearly a cycle over here, which is a problem. So like even if P4 gave up some resource which P2 is waiting for, now it's a problem that it's a cycle. So this is a bad scenario, isn't it? You're already in deadlock. Not a good thing. Yeah, that's a deadlock for sure. Okay. So this is the more sensible one. About one process at a time until the cycle is ignited. So unfortunately, we do not have a rollback mechanism in most operating systems because, well, it is costly. So it's hard to do this stuff. So rollback is pretty easy. Like you roll back, now you know it's gonna not work out, so you don't run some of the processes. Oh yeah, so this is how it's going to be. So when you're context switching, you have all these logs, right? You can like free all of them. You can free all of them by just momentarily by doing like a condition wait sort of thing. So just freeze all the mutations that you have. Yeah, because even if you're a different process than the one who has mutations, you can still free it, right? Yeah. I think that's correct. Remix is this correct. I mean, yeah, sure, you can. What's even the log thing is just that you wait for it, right? So many things. It's not a log particularly. You don't actually have for critical sections. It's not how it works. Fine. So rollback mechanism is never there, so I don't think you can actually do it. So wait for graph. So yeah, for this one, if there's a cycle, then there's for sure a deadlock. Yeah, it seems like it. For that one, you would have to do the banker's algorithm. This makes perfect sense. Let's fix this. This makes sense, I think. Okay, cool. So there you go. Deadlock's done. Synchronization done. Deadlock's done. Locks, semaphores. So the crazy thing is done. Now this just processes threads, scheduling, and yeah, that's it. So we should do questions instead. So I'm going to go to semester store. So this is something which yeah, so you have problems basically over here. I'm gonna solve all of them. So this is going to be what? Operating systems. Oh, come on. Okay, so the net is not working. Fine. What the heck? Huh. Sign in, not now. Come on, just. Alright, so you have all these different lectures. Lecture 9 address space. Where's the quizzes? Yeah, these are the quizzes. So let's do the quizzes now. I think we should just download this thing so that it doesn't cause a problem. Okay, you know what? In hindsight, let's do this later. So I'm going to take a bit of a break, eat something, and then we'll do it. Because there's going to be, how many quizzes do we have? We have 1, 2, all these lectures, concurrency, memory API, etc. OS merged. So okay, this is another quiz. So you have 3 quizzes, and I also want to do some questions from gate or something, because then I'll be for sure like this is something I know. I have confidence. So yeah, we are more or less done reading operating systems. Okay, so I'm going to stop now, and see you guys next video.